All right, good afternoon, guys. I'm terribly sorry I'm not there with you. You know, I wish I were, but as it happens, I'm off at a meeting, and so we're just going to have to do this by remote. So today's lesson is on isotopes. I just want us to take a look here and take a few moments to remember how we can use the periodic table to get information of note. And actually, that's not the version of OneNote I want here. I want this version. There we go. So here we have from the periodic table lithium. And we should remember that this number here, in this case for lithium 3, is its atomic number. And this tells us the number of protons. And what do we call this number down here? 6.91. And of course, you're all shouting at me that we call that the mass number. And that as a rule of thumb, we can actually say this is the number of protons plus, that's right, the number of neutrons. And the result of that is if we want to actually know how many neutrons we have, we can just do some simple subtraction here. If we round this, it rounds to 7. And from there, we can say that if we have a mass of 7, we know that the protons are heavy. They weigh 1 each. So if we take away the mass of the 3 protons, that leaves a mass of 4 atomic mass units, which means there must be 4 neutrons in an atom of lithium. And that is what you were taught last year, and that is fundamentally true. Now, the thing to note is this. This is just an average. It's not always the case. Lithium doesn't always have 4 neutrons. In fact, we can have a version of lithium that is three protons and 4 neutrons. I'm going to draw the neutrons in, oh, I don't know. That's a nice color. And of course, you should all be able to tell me that lithium will have 2 shells, because it's in the second row of the periodic table. You should be able to tell me it should have 3 electrons total. So that is a typical lithium atom. And we call this lithium 7, which would be written this way. Li with a 7 up top there. And lithium 7, as we know, has 3 protons and 4 neutrons. But that's not the only version of lithium that exists. In nature, you can actually also find lithium that has 3 protons, but doesn't have 4 neutrons, that in fact only has 3 neutrons. Now, because it's an electrically neutral atom, it should still have just 3 electrons. And this is a real thing too. It would be called lithium what? Well, we'd call it lithium 6 because it has 3 protons that weigh 1 each and 3 neutrons that weigh 1 each. And so altogether, it should have a mass of 6. And we would typically write it like that. And this has a mass of 6 because it has 3 protons and 3 neutrons. So an atom doesn't always have to have the same number of neutrons. Note that if it's a neutral atom, it'll always have the same number of electrons as protons. That won't change, though of course we know we can gain and lose electrons. And the number of protons can't change, because the very definition of an atom, or of an element rather, is how many protons its atoms have. So if lithium were to gain or lose protons, it would no longer be lithium, but it can have a different number of neutrons. And in this case, we call these different isotopes. Different isotopes. And let's take a minute and define this term. Atoms with the same number of protons and we call that the atomic number, but different number of neutrons are called isotopes. So any atoms that have the same number of protons but have a different number of neutrons. So lithium-7 and lithium-6 are isotopes of one another. Lithium has two state isotopes, lithium-7 and lithium-6. One of those isotopes has 4 neutrons and the other has 3 neutrons. Both of these exist in nature, both of them are real. Let's look at hydrogen for an example. If we look on the periodic table, we should see that hydrogen has an atomic number of 1, and depending on which periodic table you look at, it'll be slightly different, but 1.007994 is the usual number you come across. So we'll put that there, which means that as a rule, we expect hydrogen to have 1 proton, and then because its mass is only 1, it should have how many neutrons? None. And then how many electrons would a stable isotope of hydrogen have? Well, there we go. It would have 1 because in a neutral atom, there's always the same number of protons and electrons. And we would call this hydrogen 1. It could be written this way, though this is actually given a name as well. This is called Protium. Now, hydrogen 1, protium, is not the only isotope. I'm worried that you might not be able to see that orbital, so I'm just going to darken it up a bit like that. Because sometimes hydrogen exists that has still 1 proton. Hydrogen can only ever have 1 proton if it's going to be hydrogen, but it can also have a neutron. Now, to be electrically neutral, to be a normal atom, it would also have to have 1 lonely little electron like that. And now we would call this hydrogen not 1, but hydrogen 2. That's right. I'm going to assume you all yelled that out. I'm going to congratulate you on being sober. I wish that hadn't happened. That's better. So we'd call this hydrogen 2, and we would write it like that. This actually has a name too. You don't need to know this, but deuterium. And the last example is that sometimes hydrogen doesn't have 1 neutron. Sometimes you can actually find in nature hydrogen that has 2 neutrons, like that. And it still has just 1 shell, and it still has just one electron orbiting around it. And we would call this hydrogen 3. That should be an N. And we would write it like that. This is a fancy name too, though again, you don't need to worry about this, called tritium. The important thing is to understand that all three of these are real, and they are all versions of hydrogen that actually exist in nature. And we call these the isotopes of hydrogen. Hydrogen 1, hydrogen 2, hydrogen 3. And they only differ by mass. And they differ in mass because they have different numbers of neutrons. Now, the thing to note is that if some hydrogen weighs 1, and some hydrogen weighs 2, and some hydrogen weighs 3, why is the mass basically just 1? Like up here, some lithium 7 and some lithium weighs 6. Why is the mass basically just 7? And the reason is because just because it's an average doesn't mean they're all equally common. Doesn't mean they're all equally common. So this brings us to the idea of isotopic or isotopic abundance. And let's talk about that. Not all isotopes are equally common. If we look back at our example of lithium, the lithium-7 isotope is a lot more common than the lithium-6 isotope. In fact, if you look at these numbers here, you can see that in nature, we do find lithium-6, and it has a mass of 6.0151 atomic units, but it only occurs about 7.59, 7.6% of the time. All the rest of the time, which adds up to about 92.41% of the time, the lithium we find is the 7 isotope. So they're not equally common. There's a lot more of this than there is of that. Now, when we go to find the average weight of these, we're going to take a weighted average. And hopefully this is something you've done. Now, one thing I'm going to mention is that we have to deal with the fact that abundances are usually expressed in percentages, but we typically don't do math with these percentage numbers as they are. We usually have to convert these to decimals. So if you want the abundance as a decimal, what would it be? Well, the nice thing is percentage just means out of 100. So to take 7.59% and make it a decimal, taking it out of 100 just means dividing it by 100. And when we get that, we should get 0.0759. And those numbers are the same, but this one we'll be able to do math with. So you should be able to do the same here, so we'll do that. And 92.41% divided by 100 should just be 0.9241. Now, you should note that if you're comfortable with this, really dividing by 100 just means moving the decimal 2 places to the left. And you may well find that that's just how you like to approach it and you're comfortable. But there's the actual calculation. Now, the average atomic weight is a weighted average. And what it means by a weighted average is that because everything isn't equally common, you can't just add these together and divide by 2. Adding them together and dividing them by 2 would mean that you're equally likely to get lithium-6 as lithium-7 in nature, but we know that's not true. We know that you're much more likely to get lithium-7. So to get a weighted average, we're going to find the atomic mass, average. And the way we show average in math is often with this little bar. This little bar here means average. And what we do is this. We do indeed add them all up, but we have to multiply by how common they are. So we take the mass of an isotope and we multiply by its abundance, by how common it is. And we're going to do that for all the isotopes and add them up. And that's what this symbol means. This symbol here is a Greek letter sigma, and it means sum. And if you're not entirely clear what the word sum means, it just means add all together. So for each of these isotopes, we're going to take how much it weighs and multiply it by how common it is. And that'll help us find the average atomic mass. So the average atomic mass of lithium then would be this. Well, first we have to take the first lithium isotope, and it has a mass of 6.0151 atomic mass units. And its abundance, how common it is, well, is at 7.5%, and as a decimal, that would be 0.0759. And that is going to tell us the story for the lithium-6 portion. Then for lithium-7, that's quite a bit thicker than I did it to be. For lithium-7, we can put those numbers here. And remember what we do with each individual isotope? We just add them all together. Lithium-7 has a mass of 7.0160 atomic mass units. And it is 0.9241%, 0.9241 in abundance, which means 92.41% abundance. And then this should let us find the average atomic mass of lithium. And I want you to get in the habit of doing this in one step on your calculator. So we should be able to say 6.0151 times 0.0759 plus 7.060 times 0.9241. And when we put all together, we get 6.94 atomic units. And I would note that if you go look at the periodic table entry for lithium, its mass is 6.941. So that average worked. So because lithium-7 is much more common than lithium-6, when we take the weighted average, where we multiply the mass by the abundance, that's the number we get. All right, and I want to show that this can sometimes be a nasty process if you've got isotopes, but just because it's nasty numbers doesn't mean it needs to be confusing. It might not be a terrible idea at first if you're not super comfortable working with abundances as decimals, and add on to this. So I'm gonna add to this table, and we're gonna look at the different isotopes of iron. And there's actually 1, 2, 3, 4 different isotopes of iron that are all stable. One with a mass of 54, one with a mass of 56, one with a mass of 57, one with a mass of 58. Now we have to use the actual carefully measured masses here, but they're not equally common. You can see that iron 56 is by far the most common one, and that everything else ranges from 6% all the way down to less than a quarter, well, just about a quarter of 1%, so very low. So let's take a look. What does 5.85% become as a decimal? Now, hopefully you all shouted out, but yeah, 0.0585. What does 91.75% become? That's right, 0.9175. And 2.12%, 0.0212. And lastly, 0.28%, we gotta be careful here, 0.0028. And there we go. So now to find the average atomic mass is kind of clunky, but it's not a big deal. We're more than capable of doing it. We can say the atomic mass of iron take as an average will just be, like all the other ones, the sum of its abundance, the sum of its mass, is how we wrote it above, times its abundance for each of the isotopes. Now, this is going to be a little bit tedious work because there's 1, 2, 3, 4 isotopes, but that's okay. We can do it. So why don't you take a minute and try the calculation yourself. You can pause this video, and then we'll come back and make sure we did all the same. All right, so if we look here, our first isotope has a mass of 53.9396. I'm going to mention here something you haven't seen before, but the atomic mass unit is sometimes written with just this U as its symbol. And its abundance is 0.0585. All right, that's the first isotope taken care of. Then sum means add together. So we're going to add the next one. And it has a mass of 55.9349 and an abundance of 0.9175. That is our second isotope taken care of. And then sum means to add all together. So we're going to add the next one. It has a mass of 56.9354. Has an abundance of 0.0212. And we should be able to just fit this on the page if we're careful. I should put units with these, by the way, so I'm going to do that. And the last one has a mass of 15.9333 atomic mass units, and it has an abundance of 0.0028. Now again, kind of clunky, but not hard math. So let's just make sure we're being careful here, typing it into our calculator, 53.9396 and 0.0585 plus 55.9349 times 0.9175 plus 6.9354 times 0.0212 plus 7.9333 times 0.0028. There we go. Punch everything into our calculator. And if all goes according to plan, we get the right answer. So check your math, make sure you get the same that I got. And if you don't, be aware that it's just as likely that I'm wrong as you are. But of course, I will check this before I actually post it online. And we should get an average mass of 55.845 atomic mass units. There we go. So hopefully that makes sense. Hopefully that doesn't give you any major trouble. I left you with a bit of homework to just practice this, just to make sure it's a skill you get. I did want to show you, by the way, that when we actually go to the periodic table and look this up, that was a much bigger picture than I was anticipating. Interesting. Let me try this again. One moment. Oh, can I just do this? Hey, I can. Okay. There, so you can see iron does indeed have a mass of 55.845. And there it is. So there's some homework to practice with this. Good luck. I'm sure you will do great. Ciao.